Yeah, so we're going to do a deep dive into merge sort, and it's going to be math heavy. Just so you know, I think that your tolerance for this, I understand the limits of your tolerance for this kind of notation. But let me just say this. At the beginning of the semester, this was kind of like a well that you didn't know how deep it was, like more math after math. This is going to be, I'm not going to do any new math. I'm just going to use it extensively. And once we understand how to apply that math to merge sort, we will then be able to take on a more complex algorithm called quicksort. And quicksort does not have a big theta. Quicksort has a big O and a big omega that are different. So we have to figure out like what on average does it do. So it'll be our first of 2 average case analysis, and we're going to need the kind of math we are doing. Now, if you look at the presentations folder of today, you'll actually see the PDF. I certainly appreciate people getting getting ready to take notes. There's something to be said about writing it. I encourage people to do that, but there's actually a fallback plan. Yeah.
I was going to say, could you do another example to provide people out?
Oh, you mean with the quiz question? Yeah, like yeah, sure. Let's start with that one. Yeah. Just among friends here, I just want to level with you a little bit. I think that when you see all this stuff that happens here, like a lot of summations, recurrence relations, and so on, I'm looking for a little bit of validation in the sense that you'll say, like, you know, I still don't like this, but this doesn't intimidate me anymore. That's where I want you to be. So yeah, and again, like I said, the presentations folder contains the PDF for today. Cool. So Faith wanted me to do an example like we did last time. Yep, absolutely. Let's see now. I'm going to do this in a controlled way. So here's 1, 2, 3, 4, 5, 6, 7, and 8. And let me actually try to permute this in a reasonable way, not too much, not too little. So I'll put my 4 here, and the 2 here, maybe the 6 here. Let's put the 7 here, the 1 here, the 3 here, and then the 8 and 5. Okay? So now we are given this as the initial array. It's somewhat random. That's actually random, yeah. What we are doing is the following. I just give the gist of it. Initially, every time you are doing a merge, which means that you have 2 lists that are sorted, you pay attention to how many numbers, as you pull in a number from the right array into the merged array. As you do that for each number in the right array, how many numbers are yet waiting in the left array? You increment the counter by that number. At the end, the total gives you a measure of how much work merge sort did. Okay? So when all the recursive calls get done, we have basically these are all in individual boxes. So we're going to do an array of 2 from these 2 things. And you see how I did this, yeah. Right? So when 2 moved over, okay, so at this point, this is my left array, this is my right array. When I'm moving 2 as the first element of the merged array, there's one thing waiting to be yet merged. So that gives me a measure of 1. So then the next thing is going to be, so there's a 2, there's a 4. This is now generating from 2 lists of length 1. This is the left one, this is the right one. I'm producing a single list of 2. This one actually just comes straight down. So as this element from the right array comes, it didn't cross over anything. So that's a contribution of 0. Same with this one. Contribution of 0. Something happens here. contribution of 1. And a contribution of 1. So far so good, right? After this, it's the same thing. You just have to deal with larger arrays. So what would be the arrays of the next size?
So it'd be 4.
Mm-hmm. This will be the left array, this will be the right array for this guy.
Yeah.
This will be the left one, this is round for this guy. Okay, so we have a 6 here and a 7 here. Tell me what happens.
I think they'll all just come right down, so no contribution of strength.
Very good. I really did a number on myself. Yeah, same thing happened yesterday, right? Okay. And then finally, something interesting hopefully happens here. So 2, 4, 6, 7, 1, 3, 5, and 8. So what happens here, Faith?
Okay, so 2 is gonna move to its.
There's a 1 here.
Oh, so do we always start pulling from the right array?
The way you implement this is you have 2 iterators both at the beginnings of the list, and they're all comparing what they're pointing to, and the smaller one moves to the target, and then it advances.
Okay, so if we move 1 first.
So that actually is this whole journey and a contribution of?
Because the 4 things are waiting.
Yeah.
Yeah, okay, so 4.
Yeah, so this is going to be a contribution of 4. And the next thing?
We can move in 2.
So this moves here, this is, yeah, this is good. So 2 comes here. So now you're comparing 3 and 4?
3 and 4, then 3 comes in.
Mm-hmm.
But since, how many things are waiting? 3 more things are waiting in the left array.
Very good.
Okay.
So 3 is here, and then 4 comes down. You know, nothing happens then. So you're looking at 6 and 5.
5 comes in first, and
Very
since
good.
2 more things are waiting, so it's a contribution of 2.
Okay.
Okay, then 6 just comes right in.
6,
7,
7, and then 8. Yeah. The result would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah.
For like the last step, right? Wouldn't there be I'm kind of confused how we got 3 and then 2. Is it
Oh, these 2?
yeah?
Yeah, I can do my best to explain. And Faith, check my work here, so I can send you so you can see it. So this 3 is not that 3. This 3 means that as this 3 was actually taking its place here, there were 3 numbers in the left array yet to be brought into the merged array.
Oh, okay.
That's why it's a measure of how unsorted things were. Because it really, this should have preceded all of these things, so all of these things is a measure of how chaos there was.
Can I clarify the question? Why did we only count on the right and left?
Because when you say that, if you're sorting numbers and it's 2, 1, not 1, 2, you could say that 1 is on the wrong side of 2, or you could say 2 is on the wrong side of 1. One of them is enough to express that inversion. When you see both, one is redundant, so you would be over counting if you did both. Yeah.
I was just gonna say, for me, the easy way to think about this was in that programming sense. So the counter, if you think of how you would actually implement this, you basically have a counter, right? There's your I forgot the technical term, but the amount that it needs to be inverted.
Mm-hmm.
And that counter increments whenever you grab something from the right array by the current size of the left array. So you would have count plus equal left array dot size, because as you're pulling things out of the left array, that one is shrinking, and that's how you measure for when it's gonna be 4, 3, 2. So if that helps you, that might be another way to think about it in actual, how you would code it.
I see the value of it as a concept. In practice, the array is not shrinking, you're just moving an index over.
Well, but when you call a size, you'll still get you're not pulling from is what you're saying.
Yeah.
But if you did increment it to pull from it. then
What you could
have-
do is actually, it would be the size of the array minus the index.
Yeah.
That's
you
the
could do
number
that,
of things
yeah.
left over. Yeah. Yeah, good. Now, when I actually, so I'm going to send out a survey of movies. Jagrid, where are you? I'm going to keep you out because I think that some movies that are always safe bets for inclusion, like Lord of the Rings, Star Wars. I think that has everyone seen Lord of the Rings here? No?
Can we just stop the class?
Here's your homework. Get the DVD set, the director. Now, have you
What's
seen
the
Star Wars?
exciting edition? Oh my God.
Is there anyone who hasn't seen Star Wars? You know what, you have been a fun class. I will let this one slip, like, okay, so, I don't know, like, I guess we'll go with that list that we had
I have
yesterday.
enough
give up on the
reference for
class.
Big Bang Theory.
What?
I have enough reference for Big Bang Theory.
Yeah, how much of the movie do we need to know?
I think that if it's less than 10, so what I'm looking for is like which two individuals are most similar to each other in terms of their preferences. If it's less than 10 movies, most people will inevitably be similar, because how many ways can you sort 3 numbers?
It will be one movie, not a franchise. Because when you say Star Wars Over the Rings, that's a franchise. And like obviously, like A New Hope is a different comparison for me than a Phantom Menace. So like you would just put one movie on the list, right? For when we're drawing comparisons, you're not gonna put just the whole franchise, I'm assuming.
I'm gonna make ice cream flavors. Not movies. Yeah.
But also, it would be, I feel like it'd be valuable data if we haven't seen it, because then it would just be at the end of the list, because then we're not comparable.
I appreciate your earnest and actually quite useful attempt to make this work out. I swear to God, I'm gonna go with ice cream flavors. Yeah, yeah.
You should add a like problem in the problem set about one of the movies you would.
I thought you were gonna say I never had ice cream.
What
Then I
if
was
we-
gonna.
What if we just do our favorite numbers? Like a real math class, we can just do our favorite numbers.
I only have
Zero
like
to
2
10.
flavors of
Oh,
ice
it just
cream,
has
so
to be
that.
one.
Oh, wait. That's not bad.
Yeah, everyone should have a favorite.
I love
ranking.
19. I love 19.
2 is the great. Yeah. 2 is the best.
What's the
Such a
range?
weird
Sure,
number.
sure. That's it. That is it.
What's the range?
It'll actually show how nerdy we are, but it's gonna be. But like last person to say something, then we go. Yeah.
Oh, I actually have a question about this.
Thank you.
So yesterday you said that the amount of like flips are, or like the total score, the total
Yeah.
like, score of like how chaotic it is bounded by n squared
And squared over 2.
and squared over 2. Okay. Sorry, I'm dividing 56 by 2 in my head. No, I think it's still right.
Okay.
Because I think it's actually n log n. I don't know why, but I did like 8, 7, 6, 5, 4, 3, 2, 1, and it's exactly 28, which is 7 times 4.
Hang back after class because you're the only one asking that question, or maybe 2. Yeah.
So, if we're comparing for the second to last step, if one from the right is coming out and there are 4 left in the left, can you just say the same if you were to compare the ones taking out of the left, there are 4 left in the right? Would you get the same?
I would get the same answer. Yeah.
Okay,
Yeah.
so it doesn't matter.
It doesn't matter. Let's go with this way because yeah, it'll make things easier for us. But yeah, and for you, that's
Actually, in this case, n squared over 2 and n log n are the same number.
in
So,
this case.
In this case.
Oh yeah. Good. All right, guys. So yeah, who asked this question? Faith, you're good.
Yeah.
Okay.
Just ask me.
I'm gonna feel like a professor today. Yeah.
So you're saying you don't normally feel like a professor? That was an implication.
It was just a dumb joke, man.
What do you normally feel like?
That drummer. So the quiz question for today is going to ask you the recurrence relation of an algorithm you know. So I just want to make sure that you actually look particularly carefully to this first letter. I actually genuinely feel like a student. This is not a joke, because every time I teach, I figure something out. So it's actually that's the greatest thing one could feel like. So when we are merge sorting, that means that you are sorting n things, and this function t is telling us how long it's supposed to take, and we don't know the answer. It's basically how we are asking the question: how many steps will it take? So it's basically an asymptotic complexity measure, but it's proxy for time. Which is saying that if someone gives me a list of n things to sort, I know I'm going to have to make 2 recursive calls, right? Each will come with its own cost, but each recursive call will get half the number of numbers. And then this is the merging part. So if I have a sorted list of n over 2 length and another list of n over 2 length, To merge them, I will do n over 2 plus n over 2, which is n. So this is the cost of a single recursive call for half the array. This is because I'm making 2 recursive calls. And once the divide part of divide and conquer comes back, this is the cost of the conquer part. And we did this in this class at the beginning of the semester, but I would not actually just take it the wrong way if none of you remembers it, because some of these things you have to see it multiple times. And so is everyone okay with the first one? And I'll say something about the second one also. Yeah.
I'm just trying to remember, because I'm assuming this is the cost of merging 2 already sorted pieces of arrays, like you're bringing them.
Yeah, yeah. Like these are erased now, but like I had 2 things and the arrows were coming down.
Yeah.
Yeah. What's the last one for?
Base case.
It's your base case. It's when the array size goes down to 1, you say that I don't have to do anything, this thing is sorted. Like how can you unsort a single number, right? So that's basically, if the array is length 1, you do it in 1 step, which is like, look, I don't have to do anything, that's your O1. Everyone good with this? Yeah.
I'm kind of like, I kind of like just forgot like what is like the T of n? Like
So-
what's that like notation?
The n is the size of the array.
Mhm.
T is not as a stopwatch, but in terms of like counting fundamental operations, like a Toby Dragon type. How many steps will I take to
Okay.
sort the whole thing? It's a function that tells me that answer.
Okay.
Yeah, but it's not answering anything. I'm basically asking a question right now.
Okay.
Yeah.
Also for the, okay, I guess for the second one, you meant like n is equals to 1, but could the time complexity of n things also equal to 1 if the list is already sorted?
Say that again.
Because in this case, T of n is only 1 item, right?
Yeah.
But I'm saying could the T of n also equals 1 in this case whereby the list is already sorted? We just give it a sorted array.
Well, by the time I actually hit the case where I have to sort one thing, I am still in the sorting phase. So I drill down, and a final recursive call ends up getting only one thing to sort, and it says, I'm not gonna sort anything, this is done, right? That attitude is your O1 step at that point. Yeah. Okay, so did anyone find the PDF? I just wanna make sure that people who have access, who wanna have access to it, like in the presentations folder of the class, did anyone find it? Just one confirmation. Okay, awesome. So hopefully this actually answers all the questions, like what is the definition of these things, okay? Now, what we are doing is, this is called a rewrite style to bring this to a closed form. So when you have a summation, that thing was not in closed form because it tells you the work you have to do, but it doesn't give you a nice simple answer. So we have to do math to bring it to a closed form. When you have recurrence relations, you have a different flavor of the same problem. It actually is telling us what's going to go on, but it doesn't give me a convenient answer. So here's my way to actually bring it to a convenient answer. I say, so this is what you tell me, right? Let me actually take this thing that's in red, and I want to rewrite it. So if T of n is this yada, 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 then how can I rewrite this equation for T of n over 2? And if you are actually having a hard time wrapping your mind around this, think of it this way. You are in Microsoft Word, copy, paste the whole thing, and then search and replace every n with n over 2. So you're just rewriting it for a smaller initial array size. So that would mean that T of n over 2 is 2 times T of n over 4 plus n over 2. If you get this, I think that you're going to get the next 3 slides fairly standard easily. So it's this equation rewritten for an array that is half as big. Everyone good? Okay. So then what I do is I say, oh, okay, let me see what happens if I plug in this thing there. So then you get T of n is equal to 2 times, remember that I'm actually bringing this gray thing into this red thing, so that's why there's 2 of them. I put it in, do a little bit of algebra, and what I end up showing is that the time it takes to sort, to merge sort n things is equal to 4 times, not 2, 4 times the time it takes to sort an array a quarter of the size plus 2n. So this part is algebra. Hopefully you don't have to worry about this. It's basically going from here to here and then rewriting the original equation. Everyone good? Awesome. Okay. So let's do this again. I'm going to basically say, remember how this is equal to that? I'm going to start the next slide with it. So that's equal to that. So let's play this game one more time. I'll have 2 more iterations, then we'll look for a pattern. If T of n is equal to 4 times T of n over 4 plus 2n, let me rewrite T of n over 4. So this time, copy, paste, replace every n with n over 2, and then do some algebra to clean it up, this now equation rewritten with n over 4 being replaced with n over 8 gives you this. Take this, plug it into that, do a little bit of cleanup, and you get this. T of n is equal to 8. Remember how it was 2, became 4, now it's 8. N over 8, that was also 2, became 4, became 8, plus 3n. You're seeing a pattern, right? Like one of them is going up by powers of 2, the other one is linearly growing. This is the actual work being done, by the way. This was the cost of the merge part. Last time, I'll take this and then apply it to the next slide. T of n is equal to 8 of all that. Let's rewrite T of n over 8. Plug it, clean it up, and T of n is equal to 16. We had expected that. Time T of n over 16 plus 4n. I'm going to summarize all these things down. Right. This really hits us heavy on the head. Like, you know, look, it's definitely powers of 2. Remember, this was the number of recursive calls being made. This is how the arrays are getting smaller and smaller, and this is how much work is being done in the merge part. But remember, work is being done in the merge part. The other one is just getting to the base cases where you actually get going, right? So, can anyone guess where I'm going to take this next?
You're going to use an I as in order to do step I and then substitute the red numbers with their I value.
Yeah. And actually one sentence, if I may interject before that, if I can actually see how far I can take this, that last version actually will not have the function calling itself. It's going to be pure and simple and understandable. So I want to see like how far can I take this down, then what you said, which is treat this as your I variable and figure out what's the largest value of I you could have. All good? So that would mean that, and this is the part that made me click like years ago when I was actually just, and by the way, I understood this for the first time, having seen it multiple times, the first time I had to lecture about it. Before then, I was just parroting things that I saw. So I thought, okay, so let me actually think about this one. Remember how this fraction tells you the size of the array you were working on? It's insane for the denominator to be greater than the numerator. Like imagine like, I have an array that's 1 over 3 long, like a third of a slide. That just makes no sense. So that would mean that the denominator is not permitted to go above n. In fact, when the denominator reaches n, n over n is 1, I hit the base case. That's how you eliminate recursion. So that now I have to say like what's the largest this can get as a function of I. So then I say, oh, I think I get it now. I'm basically asking 2 to the I is equal to n. Right? What is the largest value of I such that 2 to the I reaches n for me to hit that base case? And you know, this is basically the answer to that question is log base 2 of n. Yeah.
So the denominator of like the recursive call
Mm-hmm.
is equal to 2 to the power of whatever like step we're on, so like 1, 2.
That's right. Yeah, in fact, that's the next bullet, yeah.
Oh.
I just kind of cut to the chase here a little bit, but I think we're going to see that now. So generalization. At step I, we have T of n is equal to 2 to the I times T of n over 2 to the I plus n times I. You knew that. Everyone good? This is fantastic. So then I say, so let's see, how far can you take this? And the answer is, if you let I go up to log base 2 of n, this is what happens. 2 to the log base 2 of n is equal to n. So if log base 2 of n is the last value of I, that's when recursion actually stops. You hit the base cases. Then, and which is what I just said. So let's actually, we will try that. So in fact, I'm going to plug in, now that I actually did what Omar said, like replace this with the variable. And then let's actually plug in the last value we hypothesized it's going to go up to. So it's going to be 2 times log base 2 of n times t to the n over 2 log base. Now this looks kind of complicated, but right, like this is going to be n. That's going to be n. So n times t to the n over n, that's a t of 1, base case of single extraction, and then n log n. Do you see how n log n is emerging for merge sort? That becomes 1. You can actually say TO1 is equal to 1. That was part of the assumption. So here's your merge sort being n log n. And what people never tell you is it really was big O of n log n. If you really want to be precise, it's n plus n log n because of all the bookkeeping details that we omit with the big O notation. How many people are okay with this? Yeah.
I feel like this is like really easy to process when it's like broken down like this, but then like when you have to do it on your own, I think that's when it gets like complicated to try and figure out how to start and
That's,
begin on it.
like, this could not have been scripted any better, actually. So what's going to happen is that, we will do one more of this with quicksort. In fact, it's going to be average case, so it's sort of even nastier than this. And then we'll say, like, nobody could appreciate this. I mean, the other side of Williams Hall might. They're mathematicians. They live for this kind of stuff. But we are coding, so how many times would you want to do this? In the book, in like section 2 or 3 of chapter 5, there's something called a master theorem. And it says the following. If you have an algorithm that does a number of recursive calls, so for this one it was 2, and if the input is divided by a value, b, in this case it was 2 also, and then you could express the work being done as the exponent of n, in this case it was 1. If you have your a and your b and your c, I'm going to cut to the chase and tell you what the closed form is. So it's almost like we are earning the right to use that formula as we do this. Yeah. Okay? Everyone good? Cool. Now that's actually big O of n log n. Now, I want to delve into the second one. This is going to, just be warned, this is going to look like, you will see that the algebra is not wrong, but it's insane. Like, why the hell are you doing this kind of thing? And then remarkably, it's going to become crystal clear. This technique is what I'm going to use to prove to you that the master theorem always works. Again, earning the right not to have to do this again. Everyone good, right? That's our recurrence relation for merge sort. Let's see, Benit, what did I do there? I just want you to actually tell me algebraically what happened, but not to try to interpret why I did that.
You just divided both sides with n.
Yeah, right? If x equals y, you could divide both sides by n. You haven't broken the equality, right? Okay. So let's see, Faith, what did I do here?
Just separated the equation.
Yeah, I mean, something plus something over the common denominator, you could break them up into 2 fractions. Nothing interesting. So, Fisher, what happened here?
The n over n on the right is just 1, and then you divided it.
I actually did. I regret not having done like this kind of a fraction here. So t of n over 2 hasn't changed. T of n over 2, t of n over 2.
Yeah.
But there was a 2 here, and it went down to the numerator.
Multiplied it by you just multiplied it by 1, but you treated it as 1/2 and 1/2 or something.
Yeah, like I'm thinking of 2 times 4. That's 8, right? That's actually equivalent to 4 divided by 0.5, right? So I could take this as 2 over 1, flip it, bring it to the denominator. It works out to be the same thing.
Yeah.
Yeah. So I again, why? Who knows? But is it algebraic correct? Yeah. So far, I haven't made a mistake. That's this. That's basically t of n is equal to this thing, and I just simply rewrote it. Watch this now. Jagger, what happened here?
You divided both sides by, or multiplied. You replaced n to be n by 2.
Yeah, I rewrote this equation. I replaced n with n over 2. Nothing creative, I just simply rewrote the equation. Again, why? Who knows? So, next one, Alec. Same thing, that's right. Again, it's getting stupider and stupider. I don't even know if that's a word, but it's suitable actually for this context. Like the person saying stupider is stupid. So then one more time, and then I go all the way to the end. So t of 4 over 4 equals t of 2 over 2 plus 1. Now, this entire thing actually is the answer. And there's a kind of interesting thing to note here. And I'll give you a moment if anyone wants to actually say what it is. If not, I can kind of like make it make sense. But does anyone know where I'm going with this? Yeah.
How could you like assume that the one will remain constant when you like go from t over n to t over n by 2?
Well,
Or,
and
like,
every,
the second step there.
this one?
Yeah.
Yeah, but did you notice that how each time I rewrite this actually, it's always like something divided by itself? I can show that, like that's not a mistake and it's gonna be the case. If you were to do one more of this, you will see that's the case. So watch this. For you to understand that, if I say to you, hey guys, A is equal to B, and then I say C is equal to D, you don't know what they are. I can actually carry out this addition. I could say that based on that, A plus C must equal to B plus D, right? I could do that, like we have no idea what the numbers are, but that's not incorrect. And if then someone tells me that these two things were equal, I could knock them out from both sides. Like this is basic high school algebra. I'm just saying it without giving you numbers. If you sum up all of these things, it's bound to equal to the sum of all those things. Right? Just like A equals B, C equals D means that IA plus C is equal to B plus D. I just have a bigger, fancier version of that. Yeah?
Can you explain the jump to T4 and T2?
Because I was just, yeah, like it was initially n, then it was n over 2, then n over 4, n over 8. So this was like the last, this had to be the largest thing I could divide n by before it goes down to 1. And this was the matching thing on the left for that. It really was like nothing more than pattern matching at the very end of this set of equations. Check this out. That cancels with that, right? That cancels with that. In fact, I can keep doing this. And then what I have left is this guy is equal to that plus all of the ones that I accumulated down there. Let's recap. I started with the original merge sort equation and I did some manipulation on it that seemed pointless but correct. And I brought it to a form that lends itself to rewrite the thing as like this parameter of n is going down like geometrically. So T of n over T of n, T of n over 2, T of n over 4. But this particular form, if I write all of them, obviously if this bank of equations is equal to this bank of equations, I should be able to do equal things canceled from both sides of the equality. When I do that, the original question stands, the block of ones stand, and then there's this little bit at the end, which is T of 2. That's going to be 2 T of 1. So this basically is going to be another 1. This is going to be kind of like twice the base case, which is still the base case. And then we get this as the leftover. T of n over n is equal to T of 1 over 1 plus log n. Now you know this is going to be 1, 1 over 1 is 1, right? But remember I was looking for an equation for T of n. So if I multiply both sides by n, I get n plus n log n. So I did like 2 different algebraic derivations of the closed form of merge sort. They proved to be the same thing. But the second one actually used a different technique. It kind of used the equation against itself to cancel a whole bunch of terms so we didn't have to sum them up. And then it gives me the same answer. Okay? For those of you who might be wondering, like, is this going to be on the exam? I would be, hopefully, like, you would think that it would be fair for me to expect that you understand this, so I can ask you, like, of what happened from here to here, or you take 2 things out, missing, fill in the blank. But it would not be fair to ask this as a question on the final. Right? So is that the right like level of spiciness? Like fair, right?
If you told us you were gonna ask it and then we would
Then you would memorize. By the way, this is called difference equations. Listen to this. This is called difference equations. It's actually a thing in computer science, not done anymore because we're so consumed with APIs. But the word difference equations is surprisingly similar to differential equations. So if what differential equations is the calculus, difference equations is the summations, because we deal with whole numbers. Those guys deal with fractions. Yeah.
If it was an exam question, would it be more general for like any algorithm we looked at, or would it be specifically the merge sort equations?
Merge sort level difficulty. So that would mean that like big O of merge sort complexity kind of thing. Like binary search is actually the thing that I'm going to ask you in the quiz. That's actually much simpler than merge sort. Yeah. But remember, the point actually is not to have to do this. We're not pretending to be mathematicians. We're doing enough math to understand how master theorem is driven, and then you don't have to actually do this stuff. So the thing is, like, this actually method is called a telescoping sum. So I'll go back to this. Remember how like there was massive cancellations here? This technique in mathematics is called telescoping summing. Can anyone know why? It took me 3 years, and I literally figured this out in the middle of a lecture one day, and probably standing right here, like God knows when. Yeah.
Because the telescope like it's
You do it the other way when you're.
Okay.
So I thought that it was this. Well, JWS did not exist. But like when I say telescope, I think of this. I certainly think of this. But the telescoping,
It's a spyglass.
the one that collapses,
Jack,
right?
have you seen this movie?
Wait.
Yes.
Oh, we should add this, but no, it's ice cream stand. Yeah, okay.
It was
Yeah,
different.
so you basically, that ridiculous way to rewrite that equation initially, to bring it to a form that wasn't like, why are you doing this, even though it's algebraically correct, you bring it to a telescopable form so that you can enjoy massive cancellations, and it just basically, the residual thing left at the end is the answer, which is kind of cool. Yes?
Okay, this is one more thing on the favorite things. What if we did our favorite algorithm? Because everyone's now looked at all these algorithms. If you just put a list of the algorithms we've covered in class, and we have to rank them from our favorite to least favorite.
These are ice cream flavors, by the way. Why am I wasting class time? I will entertain this possibility. Let me see if the list is out. Because I don't think anyone's going to pick like bubble sort over Dijkstra. I mean, that would be disrespectful to the man, right? So we have to figure out the right version of this, but yeah?
I haven't eaten all ice cream flavors, just putting
I love you, man. I want you in every one of my classes. Okay. I think the quiz is about to start, actually. So the quiz question is, let me give you the question. And this is really, hopefully, take your time to think about this. Nobody should lose a point on this. It's actually a much simpler version of the first slide of what I showed you.
Which quiz is it? There's a quiz 4A and there's a quiz 4A hide.
Don't do the hide one. It was supposed to be him.
Just making sure.
And also, so I think, again, I apologize for actually giving you not as much as a week for the problem sets. Like, I'm going to release the one today, but it's going to be due Wednesday of next week. It's like 7 days. Because it seems to be happening on Wednesday, so let me accept reality. It's going to be Wednesday to Wednesday.